As we're done discussing lines and planes separately, we've also looked at intersections of lines, we've looked at intersections of planes. Well, now let's have a look at a combination of those two. So lines and planes together, how do they behave? How do they intersect? So for this lesson, we're going to look at the intersection of lines and planes, and we can face three different situations as shown in the picture. So the line can either be on the plane, as shown in line N, or it could intersect the plane at one point, which is line M, or it could be parallel to the plane, which is line L. And you can solve this different ways. One of the methods is using solving them simultaneously. And you can also use some facts such that if you have a line that is parallel or on the plane, then the direction vector of the line should be perpendicular with the normal of the plane. So you can use to check that they are parallel or they coincide or it's on the plane. You can take the scalar product of the direction vector and the normal of the plane and check that it gives you a 0. So that's one way to check. There's another way to actually solve these problems. I will just do a quick step-by-step. That's just one of the methods we will be using in the worked example today. So the first thing you could do is write your line in parametric form. And then what you're going to do is you're going to substitute the parametric form in the equation of the plane. So you'll get x equals to something, y equals to something, z equals to something in parametric form. And those expressions you'll have to substitute in the equation of the plane. And then you check what do you get for lambda. If you actually get lambda canceling out, then you're in a, so if lambda ends up disappearing, you are either parallel, so no lambda, you're either parallel or you're on the line. You're parallel if you get a logic statement, so something equal to something, and they equate. And you, sorry, this is on the line, not equate. So you're on the line if you have a statement equal to something, like 5 equals to 5, so you have a logical statement. And you would be parallel if you get an illogical statement in there, so two things that don't make sense, like 10 equals to -3. And then on the other hand, if you get a lambda equals to a number, then it means you intersect at a point. And if you intersect at a point, then you can go to step 4 and you substitute lambda in step 1 to get intersection, the point of intersection. So just to clarify, this is one way to go about this. For some of the questions, I will show really quickly an alternative method to approach them. But this first method is much more solid and it guarantees a full rounded solution. So we have a plane 2x plus y minus z equals to 3, and we have 3 lines. Each slide I'm going to discuss one of the lines, so we need to see which ones are parallel, intersecting, and perpendicular. Sorry, or on the line. So let's have a look at the 1, 2, 3, 4 method. So I'm going to take line 1, I'm going to write it in parametric form. You should know how to convert this from Cartesian to parametric form. If not, go back to the video where we discuss the vector equation of a line. So I always like to start with writing it in vector form. So I know this will be -1, 3, and -2. So I'm just taking the negation of these. And then lambda 2, -1, and 3. This is my direction vector here. And then if I want to write it in parametric form, just taking each, so I have 2 lambda and then 3 minus lambda and then minus 2 plus 3 lambda. So we're at step 1 here, and then what I have to do is substitute this into my plane. So I'm going to go and take 2. Now instead of x, I'm going to substitute -1 plus 2 lambda, and then a plus y, which is 3 minus lambda, and then a minus z, which is -2 plus 3 lambda. Now it should be equal to 3, and this is where I'm getting to like the 3 different lambda values you could get. When I expand out, it gives me -2 plus 4 lambda plus 3 minus lambda plus 2 minus 3 lambda equals to 3. And if you notice, the lambdas will end up canceling out, which is fine. It means you end up with the 2 situations, which means that your line is either parallel to the plane or it's on the plane. So let's check what we get now. If we simplify further, -2 plus 3 plus 2 will actually give you just 3 equals to 3. So you get this logical statement, which means that L1 is on the line, on the plane, sorry. So that's how you show that it's on the plane. And that's it, you don't need to do anything further. So this is a more solid method, a full rounded method to prove how the line is in there. Another way to show, so method 2, is, as we said, you can use the properties of perpendicular lines. So we know that the normal of the plane is 2, 1, minus 1. You take the coefficients of x, y, and z. And if I take it with the scalar multiple of the scalar product of the direction vector, 2, minus 1, and 3, you will notice that you'll end up with a 0. These numbers are not random, they're actually the coefficients that we got here for lambda. So when it's 0, we know that it's either parallel or on the line, on the plane. So what you can do is you can test a point on the plane and see what you get. So in this situation, I can test -1, 3, and -2. And I'll go to, because this is a point on the line. And what I'm doing is I'm testing, does it also exist on the plane? If it exists on the plane, then the whole line is on the plane. -1 plus 3 minus 2, and it should give me a 3. And if you notice, if you simplify this and so on, it will, if you notice, it will give you these numbers, plus 3 and 2. So basically, this is exactly what we did here, but instead of doing it in 2 separate steps, we're doing it all combined into 1 step. That's why this method is more whole-rounded, basically. So 3 equals to 3, so L1 is on the plane. So just to show this method works. Now let's have a look at line 2. I will immediately jump to writing it in parametric form. So this will be 2 plus lambda, 2 lambda, and -1 plus 5 lambda. And if I substitute in my plane, I'm going to get 2 plus lambda plus 2 lambda minus -1 plus 5 lambda, and I'm trying to see if it's equal to 3. Expanding out, I get the following. And the equation is going to simplify to this, and notice lambda doesn't cancel out, which means it's not going to be parallel, but I will get a value for lambda, and lambda is equal to 2. So because I'm getting something logical here, so I know that my line will intersect at a point. So now that I know it intersects at a point, let me actually find this point. And you have lambda, so going back to parametric form, we just need to substitute in there. x is equal to 2 plus 2, y is equal to 2 times 2, and z is equal to negative 1 plus 5, 2, which then gives you the point 4, 4, 9 as point of intersection. This is the best method to approach this. I'm not going to do a method 2 because this is how you should approach this question anyways. This type of question with when they're intersecting at a point. That's why it's probably better to just follow this method, especially when you don't know if it's going to be parallel and so on. You can start with taking the direction vector, and you'll notice that it's not equal to 0. So then you have to go through this method again. So might as well start with this method from the beginning. And then for line 3, in parametric form, we have it as negative lambda, negative 5 plus 4 lambda, and negative 3 plus 2 lambda. And then substituting in, I get negative 5 plus 4 lambda minus negative 3 plus 2 lambda equals to 3. Expanding all of that, we slightly end up with a similar situation to the first line. You'll notice your lambda cancelling out, and which means we're either parallel or on the line. However, notice that negative 5 plus 3, negative 5 plus 3 will give you negative 2 equals to 3, which is an illogical statement. Once that happens, it means that L3, is parallel to your plane. You can again test it out using the method 2. Taking the scalar of the direction vector and the normal of the plane will give you a 0. So you're like, okay, it's parallel or on the line. And then you take a point on the line. So a point on the line will be a 0, minus 5, minus 3. And when you substitute it into your equation, you end up with the same, should be equal to 3. You end up with the same thing, so an illogical statement here. So then you can say line 3 is parallel to the plane and not on the plane. So it's quite easy solving these questions, quite straightforward. If you follow these steps, it's easy to do. So only when you prove that the line is parallel or on the line, then you can, only when you can prove that the point, you have a lambda that exists, can you find the point of intersection. Otherwise, there might not be a point of intersection, so just keep that in mind.